Very much for inviting me. So I'm going to tell you about some fundamental things today. The fundamental symmetry aspects of chirality, essentially so that you can recognize real chirality. This has been a source of much confusion in the past, especially in the context of absolute enantio selection. That means using external fields and forces to induce enantio selection. So anyway, let's start then. We all know that chirality, meaning right or left hand, we know it means right or left-handedness, pervades much of modern science, from the physics of elementary particles through organic stereochemistry, structure and behaviour of the molecules of life. But there's much else besides: nonlinear optics, chiral systems, very important in nonlinear optics now, nanotechnology, electrical engineering, pharmaceuticals, and so on. But as far as we're concerned here, what we're interested in is that life is based on homochiral chemistry. So, of course, chirality assumes a central importance in discussions of origin of life and in astrobiology, the search for evidence of life on our worlds, if not little green men. So let's have a look then at Lord Kelvin's original definition of chirality. His definition appears in his Baltimore Lectures 1904. He emphasizes the non-superimposability of a chiral object, in our case a molecule, and its mirror image. And that's, his definition is essentially the same as what we still use today in stereochemistry. But of course it all started 50 years earlier with Louis Pasteur's demonstration that mirror image enantiomers show optical rotation of equal magnitude but opposite sign. And so here's the simple natural optical rotation experiment: an isotropic collection of chiral molecules, like a sugar solution for instance, will show natural optical activity. You put linearly polarized light in at this side, and out the other side, the plane of polarization is rotated, and if you put in the mirror image sample of chiral molecules, you get an equal and opposite sense of optical rotation. Now, what has caused a lot of confusion is that a magnetic field will induce magnetic optical activity in non-chiral samples. So you apply a magnetic field parallel to the propagation of direction of the light beam of any sample, any chiral sample, you'll get an optical rotation. And if you reverse the sense of the magnetic field, you get an equal and opposite sense of optical rotation. That's the Faraday effect. Well, let's now have a look at where molecular chirality turns up in the molecules of life, the central molecules. Proteins, for instance, they consist of polypeptide chains made from combinations of 20 different amino acids, all exclusively the L-enantiomers. So there's L-alanine, and the other 20 or so amino acids have got different side chains in place of methyl there. And each different protein has a unique sequence of polypeptide sequence of several hundred amino acids, and so each different protein folds into a unique three-dimensional structure. So first of all, you have the homochirality of the polypeptide backbone made from L amino acids can favour the production of the famous right-handed alpha helix. So there you've got a higher order chirality coming in the form of the alpha helix. And then the various secondary structure elements, helices and sheets, and all this spaghetti, the loops and turns that are connecting them, that whole lot can fold cooperatively into the so-called tertiary structure, or the fold of a native protein. And each different native protein has a distinct fold which determines its function. So there's yet another level of chirality. And then in nucleic acids, these are built from chains of deoxyribonucleotides in DNA, or ribonucleosides, sides for RNA. Only D-ribose sugars occur. So there's D-ribose, which occurs in RNA. Deoxyribose, that's with the OH missing, occurs in DNA, and so here you've got sugar rings, phosphate backbone, and then that chain can generate these famous secondary structures like the right-handed E-type DNA double helix, and it's right-handed because it's based on D sugars. And homochirality, I think we probably all believe it's a sine qua non for life's chemistry. Simple arguments are that molecules of sufficient complexity to support life on Earth inevitably exist in two mirror image chiral forms, just with their complexity. And then from the lock and key aspect of biomolecular recognition processes like enzyme catalysis, where there's chirality, there must be homochirality for efficient biochemistry. So, homochirality appears to be an inevitable characteristic of the chemistry of any molecule-based life.
Is this the life that we know it? Because if you speak about artificial life, we cannot build up artificial life on the semi-chemistry?
I don't think you can. If it's molecule-based, I think if it's molecule-based, the molecules will be sufficiently complex that they're of low symmetry. They must exist in mirror image forms. Once you've got that, you have to have homochiral chemistry. It just won't work otherwise. You can envisage, well, right.
No, I think that if you're dealing with supramolecular systems, you can envisage, let's say, two radiocytes which are enantiomeric. And then you can have, let's say, catalysis that one side can catalyze one side. The other one can catalyze the other enantiomer.
Maybe.
No problem.
Yeah, okay. It sounds
in principle, I think that the life that we know, you're right, but if you have artificial life, you cannot exclude the possibility of pursuit.
You can't exclude the possibility of anything, actually. You can have your own thoughts, and I would say my own thought is, if it's molecule-based, it has to be homochiral. That's my opinion, which could be wrong. Yes. Now, no element other than carbon forms such a huge variety of compounds, many of them chiral. No other element has such a propensity for concatenation, that means formation of long chains or rings, which is especially important for constructing backbones of biopolymers. So carbon chemistry, I believe, is essential, not silicon or anything else. I don't think there's enough possibilities with other elements. Liquid water, it's the absolutely essential medium for life on Earth. And it's not just the medium, it actually acts as a lubricant of key biomolecular processes. And I'll be talking about this in my next lecture at the end of the symposium, in fact. Protein function and the role of water. Absolutely essential. There's no other solvent can be envisaged that has the necessary physico-chemical properties.
There are some situations where you have sulfur-based organisms,
yes.
Down in the deep ocean, C4, where you have volcanic activity.
Yes.
That's not really carbon-based, is it?
Well, what are the biopolymers in them? I don't know much about them. Surely they're carbon-based, but there's sulfur stuck around as well. Is that the case?
Yes,
yes,
it's the same proteins, the same RNA, the same.
Yes, the same protein.
You're not producing oxygen, you're having sulfur as a precipitate instead of oxygen
as the output based.
So water, it's not just a medium, it's a lubricant. It's absolutely vital. It promotes like order-disorder transitions, for example, and vice versa. So I believe if life on other worlds, if it exists, will probably be based on, or shall we say, molecular-based life on other worlds, forgetting things like Fred Hoyle's black cloud or whatever, exotica. But any molecule-based life on other worlds will probably be based on a homochiral organic chemistry in an aqueous environment, even if it originated independently from life on Earth. That's my opinion. Others may have other opinions, but I think it's the opinion. I mean, this is all in the context of astrobiology, and I think professional space scientists who looking for evidence of life on other worlds. That's their sort of starting point. You have to keep an open mind. You might well get surprised, but that is that's what's in most people's minds. Right. So, what came first then? Homochirality in the prebiotic monomers or in the earliest prebiotic polymers? Well, one thing which seemed to be a problem some years ago, shown by the Orgel group, homochiral nucleic acid polymers, for example, they don't form efficiently out of a racemic solution of monomers due to what they called enantiomeric cross inhibition. But then people like Patrick Sanders came along and said, well, it could work the other way around. If this enantiomeric cross inhibition selectively inhibits formation of heterochiral polymers, then mutatis mutandis, it will selectively amplify formation of homochiral polymers. So it sort of turned the argument on its head. However, as we've seen this morning from our wonderful presentation from Mark Green, homochirality in the chiral monomers isn't essential for generating homochiral synthetic polymers. Just a tiny chiral bias may suffice, and you get these concepts of sergeants and soldiers and majority rules. And then we've had some recent results showing a small chiral bias in the form of a few percent enantiomeric excess of one enantiomer. So you have a racemic mixture, but just a small excess of one enantiomer. You can generate homochiral monomers in solid liquid phase equilibria, as Donna Blackman showed recently, or emphasised, I think, with some history to that. But something that did seem to be new, in sublimation very recently, and Cook et al. And Ben Faringa showed in sublimation you can get very high enantiomeric excesses in sublimates starting from a racemic mixture with, say, serine with just a few percent enantiomeric excess from enantiomer. Then you've got the whole business of kinetically induced amplification by autocatalytic reactions, and then enormous possibilities from crystal surface chemistry, as Mayor was telling us about yesterday. So this is the situation, and so it looks as though, really, one needs to focus, say, on how do small initial enantiomeric excesses arise? How can they arise? Because if you've got those, one can envisage all these different sorts of processes generating large enantiomeric excesses in both chiral monomers and polymers, and that's where I come in. I come in at the level of how this small enantiomeric excess could be produced by some physical chiral influence. And in fact, Louis Pasteur in 1884, he conjectured that molecular chirality in the living world, it's the product of some universal chiral force or influence in nature. And he suggested this because in his time, all the substances found to be optically active in solution were natural products, not synthetic products. Now, Louis Pasteur then started to look around for this universal chiral force. So he attempted to extend the concept of chirality. He didn't use the word chirality, he used the word dissymmetry, to other aspects of the physical world. So he thought perhaps a translation coupled with a rotation, because there seems to be a screw sense there, that could be a chiral influence. Now, but he also thought a magnetic field alone could induce chirality because it generates the Faraday effect, magnetic optical rotation. And then Pierre Curie, 1894, suggested that collinear electric and magnetic fields are dissymmetric, chiral. But, you have the parallel or the anti-parallel arrangements, and they appear to be similar to chiral enantiomers. But as we'll see, only the first one there, translation plus rotation, constitutes true chirality. That system is what I call false chirality, and the magnetic field this, it doesn't have it's not even falsely covariant. Now, to appreciate all this, you need to consider the fundamental symmetries in the world around us. Physical laws like Maxwell's equations, Newton's laws of motion, they should all be invariant under three fundamental symmetry operations: parity, time reversal, charge conjugation. Parity P, that inverts positions of all particles in a system through an arbitrary space-fixed origin. So x, y, z particle you replace by minus x minus y minus a. Time reversal reverses the directions of all the motion of all the particles. It doesn't mean going backwards in time. It just means, if you've got a particle moving around this way, then time reversal reverses the sense. Charge conjugation, that interconverts particles and antiparticles. And you'll see, doesn't seem to have much relevance in the world of atoms and molecules, but in fact you'll see later on it has conceptual significance here. And physical quantities, then, you classify them according to their behaviour under these fundamental symmetry operations. So we have scalar quantities like energy and pseudoscalar quantities. There's no directional properties, they're isotropic if you like. Scalar properties like energy and mass, they're invariant under parity, whereas pseudoscalar quantities, they change sign under parity. And pseudoscalar quantities are at the heart of discussion of physics of chirality. Then going to vector quantities, they're associated with one spatial direction, and you have polar vectors. They change sign under parity. Axial vectors are invariant under parity. Then finally you can define whether your quantities are time even or time odd, depending on whether they're invariant or change sign respectively. Time reverse. So let's just look more closely at behaviour of polar and axial vectors under parity. So, as I said before, parity essentially it inverts the system through the origin of arbitrary space-fixed axes. So you've got some point there, say a particle there, coordinates x, y, z. Under parity, it goes to this position here. You just invert all the coordinates. Now, polar vectors, they change sign under parity. So typical polar vectors are position vector, velocity, linear momentum, electric dipole moment. And under parity, say a position vector will just point the other way. That's all it means. Now, axial vectors don't change sign under parity, and the classic example would be the angular momentum vector L, or magnetic dipole moment M, which depends on angular momentum vector. So you have a rotating disk, say, its angular momentum L points in this direction, and it's defined as the vector product of the coordinates of say, if you had a particle here, and the coordinate, the position vector, and the linear momentum vector. Under parity, they both change sign. R and P are both polar vectors, so they both change sign, but that means the axial angular momentum vector doesn't change sign, and that's because parity hasn't changed the sense of rotation. The sense of rotation is not changed under parity. Right. Now, electric and magnetic fields feature prominently in the consideration. So we want to understand how they behave under parity and time reversal. And the easiest way to do this is just look at the physical system that you're using to generate the field. So you generate a static electric field from a pair of oppositely charged plates. Now, parity will exchange the position of those plates. Time and hence reverse the direction of the electric field. Time reversal has no effect because it's a static system. So the electric field, it's a polar time even vector. Now, a magnetic field, you could envisage as being generated by a circulating current sheet, or a cylindrical current sheet. Now, parity doesn't affect the sense of rotation, so that doesn't change the direction of the magnetic field, but time reversal reverses the direction of the current. So magnetic field is an axial time odd vector. So you see electric and magnetic fields, they've got opposite behaviour, if you like, under parity and time reversal. Now, back to Lord Kelvin. He made this statement, appears in his Baltimore lectures: the magnetic rotation has neither right-handed nor left-handed quality. That is to say, no chirality. So the Faraday effect has no chirality. This is Lord Kelvin speaking. This was perfectly understood by Faraday and made clear in his writings, but even to the present day, 1904, we frequently find the chiral rotation and the magnetic rotation of the plane of polarized light classed together in a manner against which Faraday's original description of his discovery contains ample warning. 1904. I think Pasteur was a persistent offender, because he was actually trying to use a static magnetic field to generate absolute immediate selection. Now, Lord Kelvin would be turning in his grave today, because even today people still confuse them. You see papers on Faraday effect, magnetic circular dichroism spectroscopy. In the introduction, they talk grandly of using a magnetic field to induce chirality. Wrong. The distinction is that chiral phenomena, like natural optical rotation, they're characterized by time-even pseudoscalar observables. And going into quantum mechanics, this means the quantum states of the system must have mixed parity and definite reversality. In fact, like the quantum states describing the left and right-handed emptiness of a chiral molecule. And as Lord Kelvin said, magnetic optical rotation is not a chiral phenomenon. The observable, actually, the Faraday observable, is actually a time-odd axial vector. It's got quite different symmetry characteristics. And the quantum states to support that are quite different. They have definite parity and mixed reversality. It's actually the opposite to chiral phenomena. This is like atomic states, angular momentum states, Jm and J minus m would give you equal and opposite Faraday rotations. For any quantum mechanics enthusiasts here, this is the realization of the mixed parity states of a chiral molecule. You just imagine, so start off with planar molecule, and just consider this, this vibration here. And you have this potential harmonic oscillator potential well, and just starting going the vibration of quantum states 0, 1, 2, and so on. But the ground state, that's got even parity. The next one up has got odd parity, and so on. And then you imagine raising the potential barrier in the middle, and this then defines these two sort of opposite-handed versions oscillating between each other through tunneling, if you like, and these even and odd parity states, they start to coalesce in the bottoms of the wells, and the definite parity states, that even parity state and odd parity state, they embrace both sides, both wells. The particle you can't localize it in either well. But if it's localized in, say, the left well, so that would be its wave function, that would be the sum of those two wave functions. So psi left is that even parity function plus that odd parity function. If it's localized on the right side, then it's the even parity function minus the odd parity function. So this is why one can say that the quantum states of a chiral molecule, which you can imagine trapped in one or other of those wells, they're mixed parity states. Parity interconverts them. Apply the parity operator to the left state and you generate the right state, and vice versa. And fundamentally here, these handed states, left and right, they're states of broken parity that are interconverted by P. The Hamiltonian itself, underlying this system, has inversion symmetry. It has inversion symmetry. But the states of the system don't, they don't have inversion symmetry. The handed states don't have inversion symmetry. And an inevitable consequence is that these handed states are time dependent, because there's always a probability for tunneling from one side to the other. This is all part of the model quantum mechanics of a two-state system. What it means, though, is, you see, time-even pseudo-scalar observables, like the optical rotation angle that are supported by chiral systems, they're inevitably time dependent. If you set up an optical rotation experiment, if you wait long enough, you'll get an average result of 0, because if you wait long enough, the system will be tunneling to the other side and back and forth. You may well have to wait longer than the lifetime of the universe, because the barriers of stable molecules like tartaric acid are probably so high that they won't tunnel in the lifetime of the universe. But in principle, pseudo-scalar observables supported by chiral systems are time dependent and will average to 0 if you wait long enough. Yes, I mentioned this briefly in our discussions in previous days. Lots of people use the word chiral symmetry and chiral symmetry breaking. Chiral symmetry breaking, widely used to describe the appearance of chirality out of achiral precursors. And people like Walber and Pedro Sintas have been pointing out they don't like that, because chirality, it's not a symmetry at all in molecular science. In fact, chirality is an attribute associated with special types of reduced spatial symmetry that enables an object to exist in two non-superimposable image forms. So much better language is mirror symmetry breaking, or parity breaking, if you like. Not violation, that's a different thing. Violation, a symmetry violation, is when the Hamiltonian lacks the symmetry. Yes?
This is because you were referring to parity and time reversal.
Yes.
You should also refer to charge reversal in order to have an equalization between chiral and mirror symmetry breaking.
I'll be getting to that later.
Okay.
That's the best bit of the talk. So I'll be getting to particle antiparticle exchange, charge conjugation symmetry. Yeah, that's what you mean. Yeah. Okay. Yeah. So. Yeah. I was just saying this again. Nomenclature. Symmetry violation versus symmetry breaking. Symmetry violations, often called symmetry non-conservation, is when the Hamiltonian or Lagrangian of the system lacks a particular symmetry. The conventional Hamiltonian is invariant under parity and time reversal. But if you chuck in, like, a parity violating interaction, like a weak neutral current, then that doesn't have inversion symmetry, it changes sign, and that's parity violation. Whereas symmetry breaking is when the Hamiltonian has the symmetry, but the states of the system don't, as we've just seen with a chiral molecule. That's not in an eigenstate of parity. So that's my usage of the word symmetry breaking. Comes from like ferromagnetism, spontaneous magnetization, spontaneous symmetry breaking, when the system spontaneously magnetizes and all the magnetic moments point the same way. You've broken time reversal symmetry there. The Hamiltonian underlying that system has time reversal symmetry, but the state has broken that symmetry, you see. That's right. So, it's worth mentioning, though, chiral symmetry breaking, it's entirely appropriate in elementary particle physics, for which you require relativistic quantum field theory, and there chiral symmetry has a rigorous definition. It's the eigenstates of direct matrix operator gamma 5. And in fact, chiral symmetry in particle physics it's an internal symmetry, what's called an internal symmetry, rather than a geometrical symmetry of massless particles, and then mass is associated with broken chiral symmetry. That's perfectly correct. But we seem to, in chemistry, we seem to have sort of borrowed this chiral symmetry breaking, and it's actually not quite the right terminology. Okay, true and false chirality. How do you distinguish genuine chirality from something that looks like it but isn't really? Now, chirality in a stationary system like a helix or a chiral molecule, that's easy to recognise. There's no dubiety, a right and left-handed helix, that's it. Nothing you can do about it. But when motion is an essential ingredient of the source of chirality, like for instance Pasteur's translation across rotation, then there's two types of enantiomorphism which have to be distinguished. So true chirality, that's time invariant enantiomorphism. So that refers to systems that exist in two distinct enantiomeric states. So they're distinct states, you can distinguish them. They're interconverted by parity, or space invert, or mirror reflection, as chemists would prefer to say. They're interconverted by parity, but not by time reversal, combined with any spatial rotation. And this true chirality will support time-even pseudoscalar observables. And a truly chiral influence can induce absolute enantioselection in all circumstances. And the reason is it will lift the degeneracy of enantiomers. So true chirality, it breaks parity P, but not time reversal T. Now, more subtle than that is what I call false chirality. I didn't mean these names to stick. I've used it in my original papers just to emphasize the distinction. Yes?
How about pure versus non-pure chirality? Pure meaning that you have just the P invariance and not T or C. Just at least for the audience to clarify, because with false you think that somehow chirality is not really.
Well,
make it even
there's
simpler.
no
What you are referring to is, if you draw, let's say, the typical pairs of enantiomers with four colors, along a stereogenic unit, you have to say to the audience, these are wrong or false enantiomers, because you have to mirror also the charges of the electrons and the nuclei. Then you end at true enantiomers. This is the message behind what you are.
No.
Yes.
No. Don't think so.
So matter and antimatter in an enantiomorphic arrangement, so let's say a mirror symmetry, are true enantiomers, right?
Well, you're jumping ahead. Let me. I haven't yet explained what false chirality is. False chirality is time non-invariant enantiomorphism. Now the system can exist in two distinct enantiomeric states that are interconverted by parity or reflection, but now they're also interconverted by time reversal as well. So that's time non-invariant enantiomorphism, whereas true chirality is time invariant enantiomorphism.
Excuse me, you're not talking about something as simple as, for example, two gauche conformers.
No.
Or actual isomers.
No. I'm actually talking about really, physical systems actually, like polarized light and combinations of fields.
Not about molecules.
No. Although it does extend to molecules. So true chirality breaks parity but not time reversal. False chirality breaks parity, but it also breaks time reversal. But overall, it's it's invariant to PT, the combined symmetry of PT. It's invariant over all. And the critical thing is falsely chiral systems do not support time-even pseudoscalar observables. So it cannot induce absolute enantiomer selection in a system at equilibrium because it doesn't lift the degeneracy of enantiomers. That's the crucial difference. So look, if I show you some examples, it will hopefully all become clear. First of all, consider a stationary spinning electron. Under parity, it's still spinning in the same sense. So you've got, they're not, they're the same system. They're not distinguishable. Okay, but a spinning electron becomes truly chiral if it's translating with its spin projection parallel or anti-parallel to the propagation direction. So here it is whizzing along, and we'll say it's spinning that way. So that's a left spin polarized electron. Under parity, you reverse the direction of propagation because that's the polar vector, but you don't reverse the sense of spin. That's an axial vector. So you've converted a left spin polarized into a right spin polarized under parity. So they are distinct enantiomers. Apply time reversal. The propagation vector, that's time on, so that reverses, but you also reverse the sense of spin. So you've reversed the sense of propagation and the sense of spin. So that's still left-handed, you see. So time reversal does not interconvert those two enantiomers. So that's time invariant enantiomorphism. Time reversal doesn't touch it. Only space inversion interconverts them. So that's true chirality. And a similar diagram describes, a circularly polarized photon, which is always truly chiral, since photons always move at the velocity of light. Now,
so the upper one is the true one. Yeah, the upper one is the true. What do you call it? Yes.
This is true chirality.
The lower one is. I thought the lower one is the false one.
No. The whole diagram illustrates true chirality. See, left spin polarized particle. Parity gives you the right-handed, which is distinct. But time reversal still leaves it left. It doesn't time reversal doesn't interconvert left and right, only parity. You see, so it's time non-invariant. Time reversal doesn't interconvert the left and right-handed forms. You see. Time reversal leaves it as a left-handed form.
So if you go to the shop, you buy a screw, buy a box of screws, they all are right-handed screws.
Yes.
Then you reverse them.
Yes.
There's no sense of T.
No, there's static. There's no motion involved in the source of chirality. There's static helices. There's no problem.
So then you call that a true.
Yeah, there's no problem when chirality is static, when motion isn't involved.
Yes, and if you take a cyclone in the northern hemisphere.
A cyclone in the northern hemisphere.
Now you go to the south. That means the vorticity, the helicity, velocity dotted into the vorticity changes sign. Yes, and I think then you have the false chirality, because then both.
If time reversal interconvert, if you've got two distinct cyclonic systems, and time reversal interconverts them, then that's false chirality.
Yeah.
Electric and magnetic fields. This is Pierre Curie's symmetric system. So, here we are, parallel electric and magnetic fields. Parity reverses the electric field, because that's polar vector, but it doesn't reverse the magnetic field, because that's an axial vector. So parity interconverts these two distinct forms. They are enantiomers, because they're distinct, and they're interconverted by parity. But electric field is time even, magnetic field is time odd. So time reversal will also interconvert the parallel and anti-parallel arrangement. So that's time non-invariant enantiomorphism. That's false chirality. So collinear electric and magnetic fields, they break P and T separately, but PT invariant overall. There's been, over the years, people have tried using, parallel electric and magnetic fields to induce absolute enantio-selection, and there's endless controversies whether the tiny enantiomeric excesses they saw were genuine or not, and probably not, and so on. But if it was a simple isotropic system, this can't do it. If you let the system reach equilibrium. But you'll see later that systems out of equilibrium, under kinetic control, it's conceivable that falsely chiral influence can induce an antiomeric excess. That gets very subtle and very interesting. And I hope very right. There's always the chance, but as things get more and more subtle, that one's missed something essential. Now, let's look at something called magnetochiral phenomena. These are very interesting new range of phenomena have come up in the past couple of decades. This is a subtle interplay of chirality with magnetism. Now here, a magnetic field B, collinear, that means parallel or anti-parallel, to the propagation vector K of an unpolarized light beam, that arrangement constitutes a truly chiral system. So this is unpolarized light. Not so, it doesn't have to be, actually can be of arbitrary polarization, but we'll keep it unpolarized so as not to confuse things. You see, under parity, that reverses the propagation direction, which is a polar vector, but it doesn't touch the magnetic field, which is an axial vector. So parity interconverts the parallel and anti-parallel arrangements. They're enantiomeric. They're distinguishable under parity, space inversion. But propagation vector and magnetic field, they're both time odd. I've made a mistake there. They are they're not. So they are, so block that not out. So they are both interconverted by T, you see. So time reversal reverses both of them. So you've still got the parallel arrangement. See, time reversal does not interconvert the parallel and anti-parallel arrangement. So this is time invariant enantiomorphism. This is true chirality. And in fact, this magnetochiral phenomena, it's led to a new range of birefringence effects involving light and magnetic fields. For example, something called magnetochiral dichroism. This has actually been observed. You pass an unpolarized light beam through an absorbing chiral molecular medium. If you have a magnetic field parallel to the propagation direction, you'll get a certain absorption coefficient. Reverse the direction of the magnetic field, you'll get another absorption coefficient, and they're different. So there's a difference in the absorption coefficient of an unpolarized light beam passing through chiral absorbing medium parallel and anti-parallel to the magnetic field. This is not the Faraday effect. It depends on chirality. You have to have a chiral medium. It's a subtle interplay of chirality and magnetism.
Well, not Faraday effect. In the Faraday cell, the magnetic field is collinear with the light, right?
Either parallel or anti-parallel.
Yeah, exactly.
Yeah. Well,
So it is in a way a Faraday effect.
Well, it's not. I mean, you need a chiral medium. If that medium wasn't chiral, you wouldn't see any difference in absorption coefficient, parallel and anti-parallel. Unpolarized light.
Of course. let's say the effect of this is a Faraday.
Well,
No.
you could actually break it down into two steps, if you like. You can
Yeah.
imagine, in the presence of a magnetic field, out of that unpolarized light beam, which you imagine as an incoherent superposition of right and left circularly polarized components of equal intensity, you'll get a slight more absorption of one than the other, so you get a build-up of one circular polarization, which then, in its turn, can be involved in natural circular dichroism. You can break it down like that. That's a two-step mechanism, but there's actually a one-step mechanism through a fourth-order property response tensor, actually, where you're not physically breaking it down into these two steps. So it is a subtle interplay between chirality and magnetism. Okay, the Faraday effect is underneath there somewhere, but it's the Faraday effect plus chirality, if you like.
Okay, the paralyzer quality. No, let's say it doesn't change the current. So this is the only.
I mean, in the Faraday effect, it's just the electromagnetic field, of course.
Yes.
And if so there's no chirality in the magnetic field as
No,
such.
that's right.
So only if you couple this to an electric field at the same time would there be some parity breaking from the external factors. And that's not the case for the Faraday effect. Now, in this example, you are talking about the example where K, just the previous example on the previous transparency, where you had K and B, the lower one, both of them, of course. That's exactly the example that you're not talking about here. So there you have a true chirality.
This is true chirality. This is a truly chiral influence, and I'm just pointing out that it's associated with this new range of so-called, magnetochiral phenomena. But what's of most interest to us is you can actually use that influence, unpolarized light and the magnetic field together to induce enantioselection. And in fact, Rickard and Raupach showed this in 2000. They used unpolarized light beam. Now, you see, they used this system here. This is a famous system. It racemizes under the influence of light, and used a long time ago using in the presence of light you have a racemic mixture and rapid interconversion. If you use circularly polarized light, you'll get a slight excess of one enantiomer over the other in a steady state. Reverse the sense of circular polarization and you'll get an equal excess of the other one. That's known many years ago. So they used the same system, but now they have unpolarized light beam parallel to a magnetic field, and they get a slight excess of one enantiomer, reverse the direction of the magnetic field, and they got an equivalent slight excess of the other. And that was a genuine observation, real reproducible observation. So that shows this arrangement has true chirality. And anyway, that could be of some significance in sort of external physical influence inducing prebiotic if you're considering circularly polarized light in the cosmos, which is a very popular theme, you should also consider the magnetochiral influence, because magnetic fields and unpolarized light are far more ubiquitous in the cosmos than circularly polarized light. Although this effect is maybe 3 orders of magnitude weaker than circularly polarized light, there's much more of the ingredients around, if you like.
Well, this one equal amounts, right? Even equally one
Oh,
and the
yeah.
other, right?
Yeah, over the entire cosmos.
No, but on Earth.
Well, no, I mean, look.
No, you mean
You've got unpolarized light coming in all directions.
yeah, but then the magnetic field will have opposite polarity in north and south. And so you're right, globally over a body like the Earth, the effect, of course, is vanishing. And you would agree? Right?
Yes.
Yes.
But in galaxies and whatnot, you could have the predominance of the field pointing one way, and if you've got light from a star, going in that direction, that will give you
But globally over the galaxy again, you would have opposite directions.
Yes. Interestingly, though, since it's truly chiral, this combination, over the cosmos as a whole, because parity is violated, if you were to add up all the magnetic fields and all the circular, all the light directions and whatnot, there will be a very slight imbalance. There'll be a slight background magneto-chiral oomph, if you like.
Yes. Quite possibly, yes. That's right.
Yes. Right. Parity violation now, what one might call cosmic chirality. In the weak interactions responsible for radioactive decay among other things, radioactive beta decay, emission of beta particles, is mediated by the weak interaction. Nature makes an absolute distinction between right and left-handed spin polarized electrons. Beta decay is characterized by I can't remember which way round it is, like left-handed electrons or right-handed positrons. I can't remember which way round it is. So what that implies is parity P is not a true symmetry of the world. So in other words, left and right-handed spin polarized particles, they're interconverted by parity, but they're not completely equivalent enantiomers, if you like. So parity is violated, they're not equivalent. Now, an extreme example is only left-handed neutrinos and right-handed anti-neutrinos exist. So that suggests that parity P plus charge conjugation C, that's particle-antiparticle exchange, is the true symmetry. See, left-handed neutrino and right-handed anti-neutrinos are interconverted by CP, parity plus charge conjugation. And only that exists, and only that exists. So that suggests CP is the true symmetry, fundamental symmetry. And that kept people happy that CP was the true symmetry for about 8 or 9 years after parity violation was discovered in the 1950s. But then CP itself was found to be violated in the 1960s. And one then falls back on CPT as the true symmetry, to bring in time reversal as well. I'll come back to that later if I've got time. Now, on to atomic and molecular physics, the so-called parity-violating weak neutral current interaction. Unified theory of the weak and electromagnetic interactions, which was developed in the 1960s by Weinberg, Salam, and Glashow, they showed that the weak and the electromagnetic interactions were just two different aspects of a deeper, unified, so-called electro-weak interaction. They showed that the parity violation that you find in the weak interaction infiltrates to a tiny extent into all electromagnetic phenomena. And one can develop this so-called weak neutral current interaction. It generates this parity-violating electron-nucleus contact interaction in the Hamiltonian. So this brings it into the realm of atomic and molecular physics. You can just add that term to your atomic Hamiltonian or your molecular Hamiltonian with your quantum chemical description of atoms and molecules. The critical thing here is this sigma dot p factor. Sigma, that's the Pauli spin operator of the electron. That's a time-odd axial vector. P, that's the linear momentum of the electron. That's a time-odd polar vector. So that scalar product, it's parity of, because it's an axial and a polar vector scalar product. So it changes sign under parity, but though both vectors are time-odd, so it's overall time even. So sigma dot p is a time even pseudo-scalar. So that determines the symmetry characteristics of the neutral current interaction. So it's a time even pseudo-scalar. So that's the quintessential truly chiral influence in atomic and molecular physics. That's the best you can get. That's the quintessential truly chiral influence. And manifestations are well known. Free atomic vapors of heavy atoms. They show tiny parity-violating optical rotations, pass linearly polarized light through a vapor of bismuth or tellurium or something. you can measure a tiny optical rotation. And Patrick Sanders, who's here in the last week, he's an expert on this. He does this. He used to make these measurements routinely. As chemists, we want to know, well, where's the enantiomer that gives you the equal and opposite sense of optical rotation? Well, you can tell me the answer, can't you?
Well, you have to mirror everything. You have to build an antimatter.
That's right. Well, it's the anti-atom. If you have a sample of the vapor of the equivalent of the corresponding anti-atom, you'll get an equal and opposite sense.
It's like in the science fiction movie.
Yeah.
The antimatter Earth is behind the sun, something like this.
Yeah. Now, chiral molecules and parity violation. Now, that weak neutral current interaction, it generates a tiny parity violating energy difference, about 10 to the minus 15 kilojoules per mole, between the mirror image enantiomers of a chiral molecule. So, tiny energy difference between those p enantiomers. And of course, there's a huge industry now has blown up trying to show that parity violating energy difference is at the source of biological homochirality and why we're all made of amino acids and not D and so on. Well, anyway, it keeps people amused. Well, so now these two p enantiomers, you see, they're not strict enantiomers anymore, because the concept of enantiomer implies an exact opposite. Well, again, you can tell me where the strict enantiomer is to be found.
Yeah,
There it is there. You apply charge conjugation as well. Or you go from there to there via CP, so it's the mirror image molecule, but now composed of antiparticles. So that now is the strict enantiomer. Those are strictly degenerate. And when I first thought about this many years ago, I thought that's fine, and that's a lovely picture there, a lovely diagram. But I thought, well, if CP itself is violated, then those are no longer strict enantiomers. There'll be an energy difference again. But in fact, it's not the case. I was able to show later, in this paper here, those remain strictly degenerate even if CP is violated, provided CPT overall is concerned. And that follows from, there's a fundamental consequence of the CPT theorem. If CPT is conserved, the mass of a particle and its equivalent antiparticle are identical. And this is from the main way people are looking for evidence of CP violation. They look at trying to get the mass of a proton and the mass of the antiproton and try and detect tiny differences that they never have. If there is a tiny difference, that's CPT violation, you see. Anyway, by extending the proof from the CPT theorem that a particle and antiparticle have identical rest masses, even if CP is violated, just extending it to the molecular case, I was able to show even if CP is violated, provided CPT is conserved, those remain strict enantiomers. So that's very satisfying, that whole scheme. Well, so anyway, having conjectured that molecular chirality in the living world is the product of universal chiral forces in nature, so Pasteur would have been entranced by the discovery of parity violation in the fabric of the universe. You know, the nothingness around us actually discriminates right and left-handedness. Right-handed objects, or whatever, one-handedness sits slightly more happily in the universe than the p enantiomer. Yeah. Now, whether or not parity violation has anything to do with the origin of biomolecular homochirality and origin of life is the subject of much debate. Okay, well that's an hour. Now, should I stop there or spend another 10 or 15 minutes on CP violation and microscopic reversibility and whatnot?
It would be probably good to give it a break first of all, and we have certainly enough time after that before Gilad starts with his talk.
So,
I think
is there a short break then? Or
we should first of all thank you. Yeah, I think.
break, and then maybe another, say,
Yes.
20 minutes.
So if somebody wants to fill up his coffee cup or something, or another food, or questions. Let's ask for questions first of all. I had a question.
Because we understand it's more hyperdynamic.
Well, you can explain that just through CP violation and the fact the universe is not an equilibrium. That's all you need.
And Barron violation.
Yeah, okay. At the time of the Big Bang, there was CP violation generating, you've got a slight excess of matter and antimatter. Because it was out of equilibrium, the excess got frozen, and the equal amounts of matter and antimatter annihilated each other. What we're left with is the